There is a region of the ocean so unstable, so energetically unpredictable, that even sperm whales, the most powerful deep-diving predators on Earth, avoid remaining there for long. Sperm whales are built for extremes. They can dive deeper than a kilometer, remain underwater for more than an hour, and hunt large squid in total darkness using one of the most powerful biological sonar systems ever evolved. Their bodies are designed to tolerate crushing pressure, near freezing temperatures, and an environment where oxygen must be managed with extraordinary precision. In almost every measurable way, they are engineered to dominate the deep ocean. But even this animal operates under a strict biological rule. Every dive must produce more energy than it consumes. A sperm whale does not descend blindly into the ocean. Before diving, it fills its blood and muscles with oxygen, storing a limited reserve that must power the entire hunt, the descent, the chase, and the long vertical climb back to the surface. If prey is dense and predictable, the equation works. The whale captures enough food to repay the cost of the dive, but in certain parts of the ocean, that balance begins to fail. One of the most striking examples occurs in the Polar Convergence, a massive ocean boundary that circles Antarctica like a shifting ring. Here, relatively warmer subantarctic water collides with extremely cold Antarctic water, creating a sharp transition in temperature, density, and ocean circulation. This collision reshapes the entire ecosystem. Currents become unstable, water masses slide over one another, and prey distribution becomes unpredictable. For a predator that depends on efficient hunting during limited dives, this instability can transform a routine descent into a costly mistake. At the surface, the whale prepares carefully. It takes several slow breaths, filling its blood and muscle tissue with oxygen that will power the entire dive. Once it descends, that oxygen becomes a limited supply. There is no way to replenish it until the whale returns to the surface. From that moment forward, every movement carries a cost. Swimming downward requires muscular effort. Searching for prey requires time. Pursuing a squid requires bursts of acceleration. Even maintaining body temperature in near-freezing water demands constant energy from the whale's metabolism. All of those costs accumulate during the dive. If you enjoy exploring how extreme environments shape the limits of life in the ocean, consider subscribing to the channel. Here we break down the science behind the planet's most dangerous ecosystems and the remarkable animals that survive in them. In most parts of the deep ocean, this calculation still works. Squid and deep water fish may be scattered, but they are usually predictable enough for a skilled hunter to locate them using echolocation. A successful capture can return thousands of calories, enough to repay the energy spent during the descent and still provide a surplus. This is why sperm whales repeatedly dive into the same hunting zones. Over millions of years of evolution, these areas have proven reliable enough to sustain a predator of enormous size and energy demand. But this balance depends on one critical condition. Prey must remain dense enough to find quickly. If prey becomes too scattered, the whale is forced to spend more time searching. Searching means swimming, scanning, and changing direction repeatedly in three-dimensional space. Each additional minute underwater consumes more oxygen and burns more energy. And certain regions of the ocean push that calculation dangerously close to failure. A hunter that weighs 50 tons cannot rely on luck. It depends on patterns. Patterns in prey movement, patterns in ocean circulation, and patterns in where food tends to accumulate in the water column. Over time, these patterns create reliable hunting grounds where the whale's echolocation can quickly detect squid or fish concentrated in certain depth ranges. But the ocean is not uniform. Squid and fish are pushed apart by moving currents, scattered vertically and horizontally through the water column. Some are carried upward toward colder surface layers, while others are forced downward into deeper, darker zones. Instead of dense hunting grounds, the predator encounters a fragmented environment where potential prey appears briefly and then disappears again. The longer the search continues, the more oxygen is consumed and the more energy is burned. The dive becomes longer, the return to the surface becomes more urgent, and the margin for error grows thinner. One of the most powerful boundaries in the global ocean lies far to the south, forming a vast ring that circles Antarctica. Oceanographers call it the Polar Convergence, sometimes referred to as the Antarctic Convergence, and it marks the place where two enormous water systems collide. On one side flows the relatively milder water of the subantarctic oceans. On the other lies the dense near-freezing water that forms around the Antarctic continent. When these two water masses meet, the difference in temperature and density forces the colder Antarctic water downward, while slightly warmer water is pushed upward, creating a steep boundary in the structure of the ocean. This transition can occur over surprisingly short distances. A ship crossing the boundary may record a sudden drop of several degrees in water temperature within only a few kilometers. Beneath the surface, the contrast becomes even stronger as currents begin sliding over and under each other, forming complex layers that move in different directions at different depths. One of the most active sections of this boundary lies near the Scotia Sea, close to South Georgia Island, where powerful currents of the Antarctic Circumpolar Current compress the front into an extremely dynamic region. Here, the ocean is rarely stable for long. Water masses shift, vertical mixing increases, and entire layers of marine life can be displaced by moving currents. For many species, this instability creates opportunity. Nutrients from deep water rise toward the surface, fueling massive blooms of phytoplankton that feed swarms of Antarctic krill. During certain seasons, the region becomes one of the most productive feeding zones in the Southern Ocean. But productivity does not always mean predictability. Below the surface, the same forces that bring nutrients upward also disrupt the deeper layers where squid and fish normally form reliable hunting grounds. Instead of stable prey layers, animals are constantly redistributed by shifting currents. For a sperm whale, the real danger in a place like the Polar Convergence does not come from cold or pressure alone. The danger emerges when the environment disrupts the delicate timing of a deep dive. Every descent follows a strict sequence. The whale leaves the surface with a limited supply of oxygen, travels downward through hundreds of meters of water, searches for prey in darkness, captures what it can, and then begins the long climb back to the surface before those reserves run out. Imagine a whale descending through the deep layers of the Scotia Sea, one of the most active regions of the Antarctic Convergence. Its echolocation scans the darkness ahead, expecting to detect the dense presence of squid that normally occupy certain depths. Instead, the sonar returns only scattered signals, brief echoes that appear and vanish as shifting currents move animals through the water column. The whale adjusts its course and continues searching. Minutes pass. Oxygen continues to drain from its reserves. Eventually, the whale may detect a target and begin pursuit, accelerating through the cold water to capture it. But a single squid may not be enough to repay the cost of the entire dive. The whale must keep searching, moving farther from the depth where it first expected prey to appear. At this point, the calculation becomes dangerous. If the whale spends too long hunting in scattered conditions, it risks approaching the moment when its oxygen reserve becomes critical. The return to the surface is not immediate. From depths of more than a kilometer, the climb can take many minutes of steady swimming. The real reason sperm whales avoid lingering in places like the Polar Convergence is not because the environment is too deep, too dark, or even too cold. It is energy. Every large predator in the ocean survives by maintaining a simple balance. The energy gained from food must exceed the energy spent searching for it. As long as prey remains dense enough and the environment stays predictable, that balance holds, even in the deep ocean where conditions are harsh. But when ocean structure becomes unstable, that balance begins to break. At boundaries like the Antarctic convergence, massive water systems collide and reshape the entire ecosystem. Currents shift, prey layers scatter, and the deep ocean becomes far less predictable than it normally is. A hunter that depends on efficiency suddenly faces a much higher risk of spending precious oxygen searching through empty water. For a massive, warm-blooded predator like the sperm whale, the margin for error is small. Its brain, muscles, and body temperature require constant energy to sustain. Every dive must return enough calories to justify the cost of the descent. This is why many sperm whales adjust their migration routes as they approach the Southern Ocean, often hunting along the edges of these unstable boundaries rather than remaining inside them. By doing so, they stay close to productive ecosystems while avoiding the unpredictable conditions that can turn a routine dive into a dangerous one. Thanks for watching. If you enjoyed exploring how the ocean really works, consider subscribing to the channel, and I'll see you in the next video.